Escape from a gravitational field. What this means is how fast do you have to throw something up so that it doesn't come back down? Right? How much speed does it have to have? Really, isn't that what a rocket scientist has to know? How fast does the rocket have to go so it doesn't fall back to the earth? And that's what it is, and of course that's the t-shirt. That's the answer. To figure out how fast we call it the escape velocity for Earth or for anywhere. For the moon, you could find out the escape velocity, how fast you have to throw something so it doesn't come back down. There's the answer. Let's see why. Excuse me. So when we figure out escape velocity, you say, okay, that's the minimum velocity, kinetic energy, same thing, right? That is required so that there's no energy left at the end. So it just gets up there and it floats outside of our gravitational field. It gets far enough away, which is a weird thing because theoretically a gravitational field would go forever, but it's far enough away that it's not going to come back down, and then it doesn't have any speed left. It just stops. So really we just hang out once we're there. So if you give something more than that much velocity, then it would keep moving theoretically forever. But if you give it less than that much energy, it'll fall back to Earth. Okay? So it's the amount you have just to get it there and have no energy left. And this is where it comes into, by the way, the negative numbers start to make sense. And you have to have your head around the idea that the negative number isn't, the negative energy isn't some physical thing that you can feel and experience. It's really designed, it's implied by the physics so that we can do the calculations. An alien on a different planet who did the same calculations might choose a different convention. Unlike mathematics, for example, which is true no matter what, this is a physics thing where it's, it's designed so that it works. Just quickly, if you hear the term potential well, when I say that, like escape velocity is enough to exit Earth's potential well. You're no longer in our gravitational field. Okay, so here's the formula. And you do need to understand how this one works. We say, okay, like everything else in physics, ET1, total energy at the start is total energy at the end. The total energy, just as you speed this thing up as it leaves Earth, right, is going to be its gravitational on the surface of Earth plus the kinetic that you give it, right? And this is the idea that you have to give it enough kinetic energy so that it leaves and never comes back. And it's so that that sum has to be zero, because at the end you're giving it just enough to get there, and anything more you get it will mean it'll keep moving. And so using the formulas, this is the formula for gravitational potential energy. This is the formula for kinetic energy. Those have to equal to zero. Just rearranging for V is all we're doing, and that's how you come up with this. So if you're looking at any planet with mass m with a radius r, and it's starting at the surface of that planet, or moon, or whatever. So, as far as black holes, really what makes a black hole black is that the V that you would calculate for that particular black hole would be greater than the speed of light. That means that light can't escape. And that's all it is. It's so dense that, you send light up and it just comes right back again. It doesn't go away. And we'll talk about black holes later. But if we were going to determine the escape velocity of Earth, well, you just use this formula where m is the mass of Earth, r is the radius of Earth. Solve for V. It's, I screwed that up. It's 11,000 meters per second. 11,000 meters per second, which is 11.2 kilometers per second. And we can just verify that, actually. Escape velocity of Earth is something you can look up. If I just went escape, I've obviously done this before. Escape velocity of Earth, and I'm just Googled Wikipedia. The escape velocity is about 11.2 kilometers per second. And that's, we calculated that, and that's true. So I'm going to check mark that one because we verified it. Not only is it something that I've sort of heard a million times, we can Google it. Wikipedia says it's true. We calculated it. Must be true. Okay? So that's the escape velocity for Earth. Okay, so that's as far as we're going to get on this video. Another short video. I'm going to stop here, and that'll be part 3.